That area should be. That's it. I think that's fine. Walk-up song. We're gonna do our cover.
Oh no, it's We Will Rock You.
But it's We Will
So we
Find
found
You.
that you found another group,
Go.
UXO. Yeah, I think we're just gonna go. I know, but one start.
First time this can happen. In case they I should have one.
We have another trip, yeah.
Maybe I'll write a little
We're not cool enough.
Alright, showtime? It is the final countdown, isn't it? Everybody sit down, please. Thank you. Teams! Breathe in.
Relax.
Breathe out. Relax. You did it. You made it to this final presentation. Congratulations. It has not been easy, but you have made it. Sleep was optional for some teams, I believe. Very good. I first want to thank our sponsor, Los Alamos judges right here that will be judging you, and also the mentors. Can you please give them all a round of applause? Quick shout out to Fred, Stephanie, and the rest of the Malloy team. Where the heck are they? Can you please clap? So I have the most important piece of equipment in my hands, the clicker, right? So this is the order. Fred, do we have the order of the teams? Or, so the way this is going to work is we've randomly picked teams here, and this is the order of the team. So Team Boom Hawk, you guys are already staged here. This is what I'd like to happen as the next team, as they are being set up. If we can have the next team that is on deck kind of gather over to this side, so they don't kind of bother people, that'd be fantastic, okay? When you're ready to come down, like Team Boom Hawk here, they have the table already lined prepped up here. Please wheel it down in front of the judges, just like this. And then, when you guys are ready, start the video, and Fred will start the clock. Okay, get there. Then after 10 minutes, judges, you can ask any questions that you like for the next 5 minutes. I will try to watch the clock, make sure we kind of keep on time. We are going to run through all 6 presentations, okay? Then after that, the judges, myself, Stephanie, we're going to go deliberate in a different conference room. Everyone can then take a bio break if they want. But we have a big survey that we need filled out by all the students. Please, please, please fill that out. This is how we innovate, is from your feedback, okay? We have to practice what we preach in this class, right? So please fill that out. It is extremely important to all of us here, okay? And then after that, you guys finish your surveys, we are gonna go outside here to the steps that lead to the Starbucks. We're going to take a big picture with you guys, with the Lannel team, with the Lloyd team. Take a big, big, big team picture. Then we're going to gather back, and then we'll present the prizes. And then the judges will present the big 3 checks at the end. And hopefully get out of here by 4 o'clock. Cool. All right. Am I missing anything? Fred, Stephanie? That's all to do. Please welcome Team Boom Hawk.
Howdy, I'm Kunj Tapiawala.
I'm Arya Shah.
I'm Jalen Palmer.
I'm Aryan Mamari.
I'm Archit Sonone.
And I'm Harsh Gangaramani.
And we are Boomhawk.
Soldiers have always dedicated themselves to protecting our nation. However, there have been over 2,000 casualties in the past 20 years caused by accidental explosions, putting lives at risk. The challenge of ensuring explosive quality and preventing instability requires immediate action. The process for manufacturing high explosives is full of complications, but the testing process is a simple one. At the end of the manufacturing process, finally the batch is tested. And guess what happens if that doesn't meet the specification? When it does get approved, we can get explosives that detonate before they are supposed to, or never do. That's where we come in, introducing the latest innovation in explosive and energetics manufacturing, Boomhawk. Boomhawk is a non-destructive and adaptive integration into existing explosive manufacturing workflows that enables real-time monitoring of explosive production quality. Boomhawk takes advantage of Mettler Toledo's Particle Track G400 sensor. This off-the-shelf tool utilizes continuous imagery analysis to deliver an accurate particle size distribution. By monitoring particle size distribution of product and detecting anomalies in real time, Boomhawk will provide recommendations on changes for input parameters to ensure high-quality batch output. This way, we're able to reduce wastage and ensure high explosive quality. Boomhawk today for a safer tomorrow.
Okay, so before diving deep into the solution itself, let's take a step back and talk about the problem. Okay, so after doing thorough research in regards to high explosives, we found that there are three major problems: excessive waste, unpredictability, and inefficiency. So what this entails is the waste that is being generated right now is way more than it needs to be. And this is costing the manufacturers a lot too much money. Unpredictability. In this industry, everything is about timing. We have to make sure that these high explosives are going off at the right time. And so if we can ensure that the quality is there for these products, then we can make sure that we're saving a lot more money and creating a safer environment. And lastly, inefficiency. Right now, the production line is way more inefficient than it needs to be. This is because sensors like ours haven't been integrated to make sure that the quality is there. And since the manufacturing is going to increase exponentially within the next 10 years, we have to make sure that our lines are ready. To tell us more about that, we have Arjun.
Here are a few design requirements that we came up with. Firstly, major size. During our research, we figured out that particle size distribution is the most important factor in explosion manufacturing because it determines explosion velocity, stability, and explosion strength. After that, our prototype should be able to monitor in real time and process quickly to reduce delays and predict deviations before it's too late. Based on the input, it should either give a green flag, which is a go-ahead, or a red flag if there's a problem. If there's a problem, it should generate automatic instructions with a user-friendly interface, and if a need arises, it should allow expert intervention or manual control. And finally, understand that explosion manufacturing is a very slow process, and producing data is expensive. And to get quick solution, if a need arises in future, we need to store the data for long term.
Based on these requirements, we considered 5 different designs. The first was the C, then dynamic light scattering, the laser diffraction, transmission allow to measure crystallinity, and our favorite, this particle size analyzer. From here, we made a decision matrix that was based on our requirements, and to narrow it down to one final design. We found that the particle size analyzer best fit our requirements as it was both fast and accurate.
Boomhawk combines a hardware and software suite into the existing manufacturing process to develop accurate diagnostics and remediation steps within the manufacturing process. To do this, we utilize advanced sensor arrays, data processing, and real-time alerts, all together to create a high-quality product. Let's take a closer look at each of these categories. For our advanced sensor array, we wanted to use advanced sensors that generate rapid data output. For this, we chose the Mettler-Toledo Particle Track G400. This is a sensor off the shelf that has real-time data analysis capabilities. It's easily integratable into the existing manufacturing process and has a high data output.
And with this data, we plan on using a series of algorithms to make useful insights. Let's deep dive into this. So I know how much y'all love algorithms. So first up, we have a state-of-the-art algorithm that we designed to track data in real time and process it as it arrives. This is really beneficial because rather than taking a whole sample and then QA testing it, we QA test the sample as it comes in, which saves time. To do this, we implement a margin of error system where, depending on the explosive, we set margins of error for particle size distribution within which the explosive is still repairable. So as long as it's within these margins, then it's okay. But if it starts approaching the margin, then that's when we pause for production and we raise an alert. This portion of the data is then passed on to another algorithm. This algorithm is customer provided, again, dependent on the explosive being produced, and it will then generate recommendations which can either be passed to an operator, to a computer for automation, whatever the customer prefers. And while all this is happening, all the data we're collecting, all the alerts we're generating is being stored in a database in the long term for long-term process analysis.
When an anomaly occurs, Boomhawk reacts rapidly. When user intervention is required, Boomhawk processes the data and provides the operator with simple to follow instructions, like add 3 gallons of water or increase the reaction temperature by 5 degrees. Simple instructions like this enable the operator to confidently and quickly react to this issue and save the batch of material before it actually goes bad.
So to help better visualize our contents, we went ahead and designed this prototype you see before you. So right here we have our kettle reactor, and then these nice 3D models here are our sensor array. Now, first the customer will input their inputs into the reactor, and then once the process starts, it will take a while. But this happens at different times. So first, a small part of the batch will actually come out before the rest does. And we take this small sample and run it through the sensor array. So using particle size analyzers, we're going to record the particle size of this finished product, and that way we can determine the particle size of that product and the rest of the batch. Now, what will the operator, this guy here, actually see when the process is happening? So you can see here we have his monitor. Right? They would give him the measurements, and then bam, there's an alert, big red in your face. What do we do? Right? That's easy because Boomhawk will take initiative in this step. First, it will stop the production. We don't want to keep producing something that we know is the wrong product. Then it will go ahead and compare the measurement data to the data provided by the customer to output steps that they want to take to remedy this problem. Now, so all the operator has to do in this situation is just follow the directions provided on the screen. We'll have to add 2 gallons of liquid A, then add 4 gallons of liquid B. Now that the formula is correct, we can continue the process without losing much. So what exactly did we lose though? Well, in the normal process, this batch will be fully completed before we ever catch this error. However, using this method, we only lose this small amount of sample that we tested. On the other hand, we get to keep the rest of the batch, which will give us all this great effective product.
All right, now let's talk about the part that's important. What impact does this have and why should you care? So to quantify the impact, we split it up into 3 categories. First, our solution increases the stability of explosions. Particle size distribution is the most effective metric to quantify stability. The more stable an explosive is, the more predictable it is, which is always good. Second, we reduce the wastage of materials. Right now, how quality assurance is done is that we over-engineer our explosive to compensate for the loss of quality. That's really inefficient because it requires A, more raw materials being inputted, and B, more output being wasted. We mitigate both of those problems and hence we save our customer money. And third, we enable efficiency in manufacturing. First of all, our solution is really feasible and can be seamlessly integrated into existing workflows without modification. And what it mainly does is it enables you to process more explosive in the same amount of time, which saves time. Time is everything. Right now, in the United States, high explosive is a really important asset, and it is crucial that the manufacturing process for this asset is up to the highest standard. And that's why, while the United States is ramping up production of this explosive rapidly, it's the perfect opportunity to implement our solution and optimize time.
And that's why we're here to ask you in joining Boomhawk's journey in enhancing national security and improving the overall manufacturing of high explosives. Thank you. Any questions?
Thank you, Team Boomhawk. Judges, this is your time.
Hi, thank you. Have you considered any environmental parameters that might have other influence on your ability to monitor the process?
Okay, so yeah, these sensors are integrated into what the machine currently has. So do you want to talk about the integration with these sensors and how it won't change much of what currently goes on in the
Yeah.
manufacturing process?
So right now, before what we got before working on this is just the entire operation. All we did was we put the sensors already where the conveyor belt was, and we started taking measurements as the output was coming out. So there were no modification required, we just added something. And then what we do is we provide data. It's up to the operator how they want to use that data, whether they want to automate their process, whether they want to have an operator look at it and stop production, it's up to them. So I think, does that answer your question? Or
So we don't expect it to change much of the environmental aspects that currently take place.
Can you walk me through your prototype here? And so where is the user input required? And
Okay.
where is it autonomous?
Right. So that will be at the very end. So everything up to, let's say, a certain point is only being autonomous. So it's going to be autonomous. The sensors, all this is flowing naturally. Okay. And after the data is analyzed and taken, the user input part comes into how to deal with any errors in particle size. So the only thing the user would be doing would be like adjusting to the instructions given to him. So everything else is already autonomous. The calculations, the measurements, the storing of data, all that is already done by our system. And if the customer wants to use a human, they can. If they want to take that data given to them and input it into a different algorithm to, automate it, that's up to them. So, but up to that point, it's already self.
So can you explain to me exactly how the sensor works in terms of determining particle size?
So this works by using a combination of the previously mentioned dynamic DLS, short for dynamic light scattering, and laser diffraction. And this also uses a couple of other techniques. That's what I was talking about when I said it was more accurate. It's because it compiles all these techniques. So these work by essentially shining a light through the particle, and then looking at the way the light refracts throughout it. And based on that, it can measure the size of that particle. And because it's doing multiple of these at once, we get a size distribution rather than a single size.
What is the particle size? What is the particle size range that it can measure?
If 5 micrometers to 2,000 micrometers for the Mettler Toledo G400 that we decided to do.
Question, for this sort of particle size analyzer, do you need to do something special to your batch in order to be able to accurately measure the particle size? Like agglomeration, and overcome agglomeration issues, does it need to be in a specific solvent or something like that?
So usually the output glucose will be in a powder, and that is usually measured using these analyzers. So as long as the powder comes out, you'll be able to go through these sensors and it should work normally.
So just taking a small sample.
Exactly, yeah, it should be a small sample.
Okay, thank you. And what if there's any unexpected problems with the chemistry? Do you think this could be integrated with another approach, or?
That's a beautiful question. So we could potentially implement that into the algorithm, right?
Yeah, again, so as I said, we have a series of algorithms that can work in collaboration with each other. So we can just add another step to the process, which can depend on the explosive. We want to make our solution generalizable because the United States is ramping up their explosive production from 2 explosives to 10 explosives. And that's why the generalizability is really helpful. And we can definitely implement that in the future. That's a great suggestion.
Hey, we got time for one more question from the judges. Team Boomhawk, thank you. left of X. Please make your way down. Team Sky Guardian, please kind of prep your way up. Thank you. Gentlemen. Very good.
In areas ridden with remnants of war, the imminent threat of unexploded explosive ordnance is everywhere. Annually, 20,000 people are killed from accidental detonation of these devices. But what if we could prevent this? Introducing UXO EXO, a semi-autonomous modular aerial system with identification and marking capabilities. With on-site deployment, the UXO EXO can maneuver up to 100 acres or 40 minutes of operational flying time. The integrated sensor array includes light detection and ranging, ground-penetrating radar, and electromagnetic induction. This sensor data is relayed back to the operator in real time and creates a map identifying the UXO's precise location, efficient, and completely remote controlled. This aerial system can simultaneously pinpoint UXO location and deploy a patented grapnel hook which supports an integrated RFID and physical marker. Our innovative system ensures a safe and efficient method of UXO detection, eliminating the need for human operators within close proximity to the ordnance. Most importantly, our system ensures a future for civilians across the world.
Howdy!
Howdy!
My name is Lohit Alampali, and I'm a sophomore in computer engineering.
I'm Manish Kulkarni. I'm a master's in industrial engineering.
I'm Tanvi. I'm a sophomore in computer engineering.
I'm Eric, and I'm a sophomore in civil engineering.
I'm Lucia, and I'm a sophomore in computer science.
And I'm Kshiti, and I'm a sophomore in mechatronics engineering. And we are team Left of X. And our product is Extraordinary Operations, also known as EXO. There's a critical need for solutions that detect, identify, and mark unexploded ordnances. So our team focused on 5 design goals, which was to create a semi-autonomous system which can detect shallow buried UXO for up to 1 meter deep into the ground. We also wanted to positively identify threats by using multiple marking capabilities, as well as implement an on-site deployment system. The 3 design concepts that we considered was the aerial delivery, all-terrain vehicle, as well as a combination of both the UAV and the ATV. However, in our team's analysis, we found out that the ATV has decreased maneuverability on the field, as well as an increase in accidental detonation on the field. Additionally, a combination of both the ATV and the UAV is an over-engineered process that can be simplified down to a simpler solution. So that's why our team selected aerial delivery. And the EXO is efficient and offers ease of operation for the operator. Now Lucia is going to explain more about our product, the EXO.
The EXO is an aerial delivery system. It's a device that can accurately, it can accurately track and identify, as well as mark, unexploded ordnances in the target areas that we consider problematic. It uses cutting-edge technology and integrated sensors that are industry grade. They're already being used in the field, and this allows us for a thorough and extensive research on the location of these devices. Our product consists on a fleet of identical drones that work in tandem to sort of divide and conquer the area that we are trying to target. They work in a cooperative nature, which allows for greater positioning of accuracy of the drones themselves. But since their pathing is determined by a computer, they have a feedback system that allows them to recalculate their path in case a drone goes off path. They are semi-autonomous. This means the pathing and execution is done by a computer, but we also have a remotely located operator that is in charge of overseeing the whole thing. The operator just looks at the pathing of the drones to make sure that it's correct, and they also verify the sensor outputs that we should be getting, which is something that Eric is going to be talking more about.
One of the most important aspects of our drone capability is the identification and detection of the unexploded explosive ordnance items that could be buried throughout the world. In order to do this, our sensor array integrates a multi-spectral imaging that allows for the integration of light detection and ranging, electromagnetic induction, and also ground-penetrating radar. The ground-penetrating radar and the electromagnetic induction is capable of sensing anywhere from a half a meter up to 5 meters above ground. And the light detection and ranging is capable of being produced from 5 meters to 60 meters above ground. Now what this does is it shoots back in real time back to the operator and creates a three-dimensional topographical map which has all of the potential hazards mapped inside of it for further explanation and exploitation. We can then take this information and compare it against known ordnance items in order for the operator on the ground and follow-on forces to be able to compare that to potential hazards that are present throughout the field of operations or wherever it is that we're searching and we're looking at. Next, Tommy's going to talk about how we're going to mark these potential hazards that we find.
So once the drone goes over and detects and identifies the location of the UXO, it needs to be physically marked so that the deminers can locate exactly where it is, and also so civilians and personnel are able to see where it is and avoid it. So for the deminer location, we're going to use a projectile from the drone. So once the drone goes over the UXO, it's going to go about half a meter above the ground and offset about 1 meter from the location of the UXO, just so it doesn't detonate it. And the projectile is going to launch into the ground, which has an embedded RFID tag to track the location of the UXO. And it's going to have a grappling hook attached at the end so that once it's launched to the ground, it stays there and it doesn't move due to any external conditions. And as for the visual identification, we're going to use a chemical marker, and it's going to be a glass sphere on the end of the projectile, which once the projectile comes in contact with the ground, the glass sphere will shatter, and the chalk powder inside of the glass sphere will cover the ground where the UXO is so that it's visually identifiable by civilians and personnel. And now Anish is going to talk about the on-site deployment.
So the question may arise, how is this going to really work? So we are implementing an on-site mobile command station, which could be a semi-truck or a Savannah or a basic Humvee. So these vehicles will have up drones and also the operation center where the operator can deploy these drones. Like mentioned by Lucia, this is a semi-autonomous system. So the operator will just have to mention the path mention the boundary that's required to be scanned, and the drones will go out and do their thing. However, the operator will also have to monitor if they are going the right track. So if a drone goes off path, the operator will have the ability to call back either the single drone or the entire fleet of drones home and then fix it right over there and send them back again. As mentioned earlier, that we have developed a modular system that allows us for resource localization. So our command station, which is basically a vehicle or a van, will have all the components and all the resources that one would require in case of a breakdown. So if the system out there breaks down by any chance, it can all be called back and it can be fixed right there and then sent back again. Further, modularity also allows us two ways of operation. If in a scenario that the land size is small and it's not too complex, our drones can go out right there and just do all their stuff, that is detection, identification, and marking in one sweep. Otherwise, if the topology is too complex or if the land that we are scanning is too large, they can simply first do a wild scan. They can go out and just detect the presence of UXO, come back again, swap their batteries, fill the cartridges that we have here, and then go back again and identify and mark the UXOs and then come back home. This way, we save on our battery energy, save on our time, and we maximize the efficiency of things. Now next, Lohit will talk about the functionality of the product.
Thank you. We love how much functionality is baked into this product. Look at it, it's a full package, it's fantastic. But to do this, we have to implement two important technologies. One, an important machine learning model that will train our UXO to predict behaviors for regions that would otherwise not be explored. This allows for greater coverage and a pseudo-random placement of mines. Furthermore, the RFID can store metadata that is specific to its access. So it'll access a database when the miners access it, and this information can be stored with any information necessary, such as location and identification information. Thank you.
I'd like to open up the floor for questions, so please.
Yes, please.
Judges.
Question for you guys.
Yes, sir.
So typically, ground penetrating radar as well as electromagnetic means of detection requires very close proximity to the ground.
Yes, sir.
How does your system address that?
Absolutely. So thank you for your question. And as I understand your question, is the relation of the drone above ground to the ordnance item, is that?
Yes, typically, for GPR to work, you almost have to be in contact with the ground.
Yes, absolutely.
The same
So
thing with an electromagnetic sensor, you have to kind of go over very close to it in order to be able to detect that anomaly that
correct.
produced on the ground.
Absolutely. So some of the sensors that we found in our exploration over the weekend have parameters between 0.5 meter and up to 5 meters above ground for GPR on a drone mounted platform. So that's where we got our information from as applicable to the system that we designed.
Hi, question. Have you gotten an estimate how much one of these like drones fully instrumented will cost, and what is the total weight of the instruments you're considering? Because it have a weight limit, of course.
No, absolutely. Yeah. So I can speak to the price, and then I can pass it off as far as that goes.
The sensors are relatively light. The drone itself that we're planning to build and implement has a weight payload about 8 kilograms, which is way above what our sensors weigh. In average, each of them is like 1 kilogram or 2. So we are working under the assumption that it flies, like it can manage all that weight. As for price, I mean, Eric knows.
Yeah, absolutely. So for the LiDAR system, the light detecting distance radiation that does the mapping for it, that's approximately between 0.2 and 0.3 pounds. It's currently being used in industry for surveying for civil engineering. So that well within that 8 kilogram amount. As far as the price on that, that's roughly $10,000. The ground penetrating radar that we were looking at is arguably one of the most expensive pieces, was around $20,000. And the actual weight of the GPR system itself was 0.8 kilograms. And then depending on which antenna you're using for different depths, ranged from 0.2 pounds to 0.2 kilograms to 0.4 kilograms, depending on how you had it set up. And again, those were both based off of drone packages that are already being used commercial off the shelf. As far as the EMI sensing technology, that needs a little bit more. All the EMI sensing technology that we were able to find that would be applicable to this platform was already integrated in either a version of the Minehound or other minesweepers. And so the weight on those would be an estimate, but it would be less than 2 kilograms each. So that's well within our threshold for our 8 kilograms for the platform that we had. And around a total sticker price with just a commercial off the shelf, depending on if there's any restrictions on country of origin for where this stuff is being procured from, was between $50,000 to $60,000 all inclusive. Does that answer your question? Okay, thank you.
How many of those are you expecting to need? Because you said you're basically sending out a swarm.
Absolutely. So the initial intent of the project was we wanted to have a complementary suite that could go on site for on-site deployment, and our initial estimate was between 5 and 10 drones, and that is for the package that we had created. Now, obviously, that's scalable, right? Depending on where we're going throughout the country, and we did a lot of research in the different countries that are laden with mines, starting with Egypt that is over 20 million, all the way to Cambodia that's between 1 and 2 million. So depending on the theater of operations in which we're going to be going to and the scalability of the product, The great part is we can just add, you can essentially add more drones. So if we start from a launch point of 10, that can be scaled up depending on the size and scope of the capability for the mission that it's going to be applied towards. Does that answer your question? Sorry, it's a long answer for a short question.
One more quick question from the judges. One more quick question.
Okay, so how do you make sure when you deploy this grappling hook projectile into an explosive ordnance device that it doesn't detonate?
Sure, absolutely. Yeah, absolutely. Go ahead.
So when we deploy the projectile into the ground, it's about offset about a meter from the location of the actual UXO so that it doesn't accidentally detonate it. And it's about half a meter above the ground so that it's not going to go out of the range that we want it to.
And of course, this is where the RFID tag comes in, because the RFID tag will hold the metadata. So obviously 1 meter away, you're like, wait, that's not where the bomb is. Well, the RFID tag can store the information, or at least give access to information that is how far away did we mark it from the actual location detected from the UXO.
It's a great question. We thought about that. There's bombs in the ground. We don't want to shoot the bombs in the ground. We completely understand. And one of the reasons why we wanted the semi-autonomous model was to allow the user or the operator in the rear to be able to make that complicated decision. Because we thought about all the different terrains this could be implemented in. If we're talking about a rice field in Cambodia or Vietnam, all the way to a sand dune in Egypt, the user has the ability to go inside and orchestrate exactly where that's going to be. If the user decides it's a 10-meter standoff is most appropriate because there's a canal or a drainage ditch, then so be it. He has the ability to do it. But our recommended would be 1 meter offset for that specific reason.
All right, thank you. Team left of X, thank you. Team Sky Guardian, please come on down, and Team Bios X. On deck.
You're getting that stick. Oh my God, the clicker. So sorry.
Bomb unexpectedly exploding in the UK. The huge blast could be seen and felt for miles.
14 people have been killed in a bomb attack on a bus carrying soldiers.
On Maui, an unexploded ordnance was found earlier this week in a field along.
Every year, it's not just one person, but a staggering 20,000 individuals who lose their lives to unexploded ordnances. These hidden threats, often found in high-risk areas, gravely endanger human life, with 80% of victims being innocent civilians, including many children. Each casualty represents a devastating loss, and the impact goes beyond personal tragedy, endangering the future and economies. The intrinsic value of every human life drives the need for a life-saving solution. The issue lies in the current methods for UXO identification, which rely on personnel placing themselves in harm's way, a process both dangerous and time-consuming. Every moment counts. Meet Sky Guardian, an innovative unmanned drone for safe UXO identification and marking. Featuring a loitering mode, a dual paint mechanism, and advanced sensors, it ensures precise identification and marking of UXOs. Sky Guardian will save countless lives.
Howdy, where's Sky Guardian?
Howdy, my name is Samika. I'm a freshman engineering major.
Hey guys, I'm Sal Patel. I'm Mechatronics Junior.
I'm Quentin. I'm a senior mechanical engineer.
I'm Aryan Gandhi, a freshman engineering major.
Howdy, I'm Kevin. I'm a sophomore computer science major.
Howdy, I'm Marshall Mann. I'm a senior in aerospace engineering.
Howdy, I'm Braden, and I'm a freshman engineering major.
So unexploded ordnances are a huge issue in today's society. Statistics that we found were over 1 million UXOs were identified in Ukraine so far, and that's obviously a huge threat to civilians nowadays. There's 75 million UXOs identified in Laos since the Vietnam War, which occurred over 50 years ago, and there's 6,892 UXO casualties in 2019 around the globe. After careful consideration of the problem, our team needed to create a need statement, which is that we need to create a system to safely identify and physically mark the location of UXOs autonomously in known mined and hard to reach areas.
So that brings us to the gaps that we found in existing UXO detection systems. First, we found that they're lacking versatility. Some of these existing systems may only have 1 or 2 sensors, and that makes them very used in only a few situations. They have a low accuracy. There's a false positive rate of almost 20%. So 20% of the time, they'll identify a piece of scrap metal as a UXO. And finally, some existing solutions are personnel intensive, so you might require up to a 7-person team to find and identify some UXOs. So we came up with 5 design requirements. Firstly, we found that we need to be able to identify the coordinates of these UXOs and then transmit these coordinates to operators on the ground in real time to convey this time-sensitive information. Thirdly, it needs to be a fully autonomous system, so an operator on the ground presses start and the drone operates and completes its mission entirely autonomously without any human input. Fourthly, it needs to have shielded electronics so that it can operate in a wide variety of environments and not be affected by electromagnetic interference. And finally, it needs to physically mark the location of the UXO, and we do this by spraying paint on the location, and that allows people who in the next stage may come in and actually remove the UXO to be able to easily identify where exactly it is.
So before narrowing down to our final designs, we had 2 designs. One is the Land Rover and the other is the quadcopter drone. The quadcopter drone was less aerodynamic, it had lesser range in terms of the distance, in terms of the time. It was not as sturdy as our final design is. The second design, which is the land-based rover, it had high-risk detonation, which means since it is in proximity to the UXO, there's high chances it might mess with it. Secondly, since it's on ground, we intend to transmit data real time, it is not as efficient in communicating the data as our final design, which is the Sky Guardian.
Introducing the Sky Guardian. This drone is the final accumulation of our design parameters and design specifications. We have decided on creating a hybrid drone that combines the versatility of a quadcopter design and the long-range performance of a fixed-wing aircraft. As you can see here, we actually have a quadcopter design combined with a horizontal flying wing design. So this design combines the effective use of precision locations such as in a quadcopter and also the long-range capability of a blended wing design. This is deployable also with a package payload that we will lower down to within 2 to 5 feet in terms of a location from the ground to actually get more accurate data on the UXO we're identifying and to actually distribute the paint which physically marks the UXO. This design is obviously safer than a rover because it doesn't disturb the ground or area around it. As well, it is compact, lightweight, as Savia just demonstrated. It is field deployable by a single operator and is also modular. We have the wings and body as separate pieces, and this also decreases our maintenance costs if we have an error in the field. A few technical specifications that we verified through aerodynamic modeling. First of all, our range in horizontal flight is 5 to 10 miles, which is obviously greater than any quadcopter or any other design that doesn't use the efficiency of a blended wing body. And also that enables a 2 to 3 square mile scan area. Our total scan time will take 30 minutes. That's how much battery range we've allotted for it. In terms of speed, we have verified that we can cruise at 50 miles per hour in the horizontal regime and 0 to 5 miles per hour in our vertical flight regime. And in terms of altitude, a mission parameter or a mission might look like 150 feet, cruising for 5 to 10 miles, and then hovering at 35 feet. And once it identifies the UXO, it will actually drop the module down to 2 feet.
Okay, so this is our 3 modes. First of all, I'm doing the high altitude recon. This is the first flight. We have the low altitude recon in your second flight and your ground scan in your second flight as well. So what I mean by that is you will have initial scan in the first flight. You will use an algorithm we built, which is sky mapping. You will use historical data to find out, okay, which is the probable location for that UXO. You will use, okay, this is the area I want to go in. Let's do the second flight in that. So you utilize magnetometer in that one, and you use ground and penetrating radars for the ground scan. There's first mode, second mode, and third mode. First one uses high-res camera LiDAR. Second one uses magnetometer. Since that one is able to operate at 35 feet, we are making it the second mode. And the third mode needs to be as low as possible. How we've seen before, it drops a module down as low as it can. It is 1 or 2 feet, and that will be having a payload, not only the sensors, but also a paint system with it. So this is our paint system. It has a pumping mechanism. We built one of them in real life, and the second one is animation for our safety. And we have 2 paints that we're using for it. One of them is more urgent, it's red paint. The second is caution, which is neon. We identify which one we use using our sky mapping algorithm. We'll show that later in the slide. But we also not only see if UXO is immediate death, we see that. We also see if the condition of UXO is good enough. Is it healthy? Is it at risk of explosion? Does it pose an immediate threat? The paint is sticky. It lasts long. It's identifiable. And not only do we have a physical marking, we also transmit real life digital coordinate, and we also back that data up in case we lose connection.
So we have developed a custom algorithm for the Sky Guardian. It is known as SkyMap, and it's developed in Python. Essentially, the user input is the known UXO locations, which change, and as more data is accumulated, these zones of interest are mapped out in graphical form, as shown on the left, and an optimal flight path is generated for the second flight. And the motivation that sets SkyMap apart from other similar algorithms is the consistent accumulation of data to optimize its flight path, which allows for future applications with AI and machine learning.
So let's talk about the commercial viability of Sky Guardian. So currently in the Department of Defense of the United States spend over $200 million annually in simply finding and locating UXOs. Here at Sky Guardian, we spend $25,000 in creating a single unit. This is a fraction of the cost that other companies spend. This helps us talk and reach out to other organizations such as UNICEF, which have a strict budget. And this also allows us to implement Sky Guardian, which essentially cuts down the personnel you need in order to find these UXOs, which means you can spend more time finding UXOs and less time finding people.
Thank you, and we hope you can help us save lives from the sky.
Thank you.
Judges.
Do you know how quickly your sensors are able to make a determination in comparison to your speed? And kind of related to that, what's the field of view as you're traffic?
So the reason why we use a cruise altitude of 150 feet, so the camera can have a wider scan. It can see for 1 square mile. It's able to see every single bit of it. And after that, if we find a probable location with our algorithm, then only then we have a flight altitude of 35, which is VTOL. You loiter over there, you see the area. That's a more deeper scan. That brings the time that I was saying. You have the time for magnetometer, and you also have time for the GPR to work on it at 0 speed. So essentially, you get a good resolution with that scan. Was that your question?
You showed us how you could recently field deploy the drone itself. What about the sensor package? Is that what's the size and weight, and how do you get that to the field and deploy it?
Right. So the sensor package is actually stored inside the center body of the aircraft. So we have a spool system, basically of string, that is able to autonomously drop the sensor payload down, to within that 2 to 5 feet standoff distance. But again, the payload is actually stored internally on the aircraft, so it's able to maintain its aerodynamics, for a very efficient long-range flight. And then once it identifies, has all the data through our algorithm and through previous scans that there's a high probability that there is a mine there, that's when we transition into the low altitude VTOL mode, where it deploys the sensor package and the paint package to actually mark the UXO.
As you go in your low altitude slow mode, do you have a general feeling for what type of crosswinds you'd be able to withstand, given that now you have this dangling basket in the bottom? Right. Very dependent on.
Right. Yeah, that's something we considered, and we actually looked into it. There are a lot of PID controllers and actually autonomous drone software that takes in a coordinate system, basically like a point map, basically that you can put on a satellite imagery such as Google Maps, and then it uses the GPS sensor on board the aircraft to actually, stabilize the drone itself in quadcopter mode, and then we're hoping to use sensor fusion, with all the other sensors physically mounted to the aircraft to then counterbalance the effect of that pendulum. And we expect to define a maximum crosswind operating limit basically for this aircraft, and we're estimating that to be around 25 miles an hour gusting. So it can easily withstand up to 20 miles an hour sustained, but 25 miles per hour gusting would be a design limit to us. But of course, you can choose any other time of the day to deploy the drone, given our sensors don't rely on time of day lighting.
One last question. The choice of colors on the paints, do you consider any other colors? Because red and orange are pretty close when they're outside and they can fade. And how long do you think it's going to take between painting and actually somebody getting to the point?
Glad you asked that question. So when we have two paints, normally we see before the algorithm if this is a known area, which is mine. Is it close to civilian villages? And when we have that data, when we know, okay, this is a red line, we relay that back immediately. The people on the ground, they will come in, detonation experts will come in. This is high priority message. So it will show up in real time in your systems over there that this needs to be dealt with and dealt with quickly. Orange is more like caution, so it could be like a mine in a rural area where there's rice fields basically. You don't go there often. And you asked a question of why we use neon orange. The reason why, being in nature, you don't see neon orange that often. We consider neon green, we consider neon yellow, neon orange. You see that quickly. Red, it's a global color for danger. You want to know you're in danger, you want to know you'll get out of there. So that's why we use red as well. And that's why we have two systems for it. One for caution, one for imminent danger. So even if you find a cluster, let's say, which one needs to be dealt with quickly? Which one of them has weak casing? Which one of them is in the pathway of a pedestrian? Which one needs to be dealt with? So that's our color choice.
Thank you. Up next, Team Biotech, and then Team UXO Minesweepers. Please gather on deck.
What?
Landmines do not distinguish between soldiers and civilians. Across the globe, they pose an unavoidable risk to human safety. Biotech tackles this problem by uniquely identifying landmines through biotechnology. The majority of landmines are made with TNT, which degrades into DNT, which when left dormant penetrates the device's housing and seeps into the surrounding soil. Biotech begins in the air, where an autonomous airplane disperses particles of genetically modified bioorganisms, similar to how crop dusters fertilize farmland. The bioparticles land on the ground, and the explosive chemicals leaked from the landmines seep into the permeable surfaces of the particles and activate a visible bioluminescence. In the darkness of night, a second pass of a close-ranged quadcopter uses camera imaging to detect the fluorescent patches on the ground surface and record precise GPS coordinates of the landmines. This is used to produce precise mapping of the landmine locations, enabling authorities to handle them in a controlled manner at a later time. Remote autonomous operations remove the need for human interaction to provide safety and scalability. The future of remote landmine detection starts with biotech.
Howdy, we are biotech using biotechnology for UXO detection. I'm Tim.
I'm Tor.
Alec.
David.
I'm Aiden.
McCrane. I'm Austin.
Our problem statement is that current landmine detection technologies are unsafe, inconsistent, and inefficient. Now let's take a step back for a minute and consider why landmines are such a threat to our current society. Not only do landmines pose a serious risk to both life and limb, but communities who are directly adjacent to known minefields that have been marked off previously often do not even step foot into those minefields, causing problems where they're not able to reap the resources of the agriculture around them, causing problems where they have potential shortages of food and or water.
So going off of what Tim said, our product requirements are designed so that they take into account safety, consistency, and efficiency. Our first product requirement is autonomous UXO detection. We want to ensure efficiency, but also not risk someone's life out on the field. Second, positive response accuracy. We want to minimize the number of false negatives so that we don't risk someone's life on the field, while also minimizing false positives so we don't waste someone's time and we're more efficient. Third, terrain adaptability. Landmines can be found in many places. We want to be consistent on different terrains so that we can get them all. Fourth is location marking. We want to mark it on the GPS so that people or the bomb squad can later go on and can then safely defuse the bomb. Lastly, we have no detonations. Our goal is to find the landmine, not to defuse it. We don't want to accidentally end up blowing up a bomb. Now I'll hand it off to Alec, who'll talk about our designs.
Thank you. So for this high-stakes situation game of hide and seek, we developed 3 unique solutions. The first solution we considered was a quadcopter drone design equipped with an arm. This arm would enable us to do very close image sensing for sensing technologies such as ground-penetrating radar or magnetic sensing. The second design we approached was a dual deploy system, first using a swarm of drones to use infrared sensing to detect mine hotspots. The second part of that design would release rovers to then go pinpoint the exact locations and mark it with GPS tracking units. The third solution that we came up with was a way to leverage modified biomarkers to react with chemicals commonly found in UXOs, specifically landmines, and then a second passover with a low-speed air vehicle to scan for these images, process this data, and precisely mark their locations using GPS.
Yeah. So to compare these 3 methods, the first method where we use a drone and then drop down an arm, we found that to be unstable and very hard to determine the flight time, making it unreliable for us, as well as causing a weight constraint, meaning the types of sensors that we could use, such as a ground-penetrating radar, would be very limited, as well as the fact that maintaining autonomously the height that we would need for proper readings would be very unreliable and hard to maintain. And that leads us to our second method, where we utilize the 2-pronged approach, in which case the main issue was that the rover would not be able to cross large bodies of water, meaning our range would be very highly limited, which leads us to our third approach, which effectively mitigates all of these issues by being able to fly over and not use any other land methods and have a much wider breadth. Let me pass it on to Aiden to talk more about this.
Yeah, so this is our entire system design here. So like we were saying, first we'll go over with a unmanned aircraft, dropping off the particles while we do that. After about 5 hours or so, the particles will be fully illuminating out blue light, of which we'll send an unmanned drone to go take photos of this. Now, the way we have it set up is we also have a base camp situated around the area for both proximity, and we have high quality GPS markings there. This now also works with the GPS satellite network to give us inch level, near inches of accuracy when marking locations of our both of the drones. Once we're done taking photos of the entire area, we'll take them off of the drones and offboard them to our database. And the database will then look through it all and say, well, where is there potentially a landmine? And then it will also work with the sensor data from that high quality GPSs to then locate and record all of that. And to talk about the chemistry of the particles, pass off to Agro.
Yeah, so these, you might want to know what the particles are made out of. And they're made out of bacteria that you can commonly find in your yogurts, E. coli. Now you might be wondering, why in the world would we use E. coli? Now there are thousands of strands of E. coli, but the E. coli strands that we are utilizing for our solutions have been researched and tested to not have any harmful effects on humans as well as the environment. In addition to this, these genetically modified and engineered E. coli strands have been specifically tailored to detect TNT and DNT, which are commonly found in landmines around the world today. Now, we aren't just going to spread E. coli around random land areas. We are going to encapsulate it within a solid gel-like substance known as alginate. It is a biodegradable and biocompatible substance that allows our particle to be eco-friendly as well, so that it doesn't harm the environment in the process. And when the particles are dropped onto a surface area of land, when it does come in contact with the landmine, it will absorb the DNT and TNT, and when that happens, it will emit a blue light as a fluorescent, which will serve as a biomarker for. And now to describe how we visually analyze and process these blue lights, I'm going to hand it over to Austin to describe that.
Absolutely. So we are taking full advantage of the bioengineering of this E. coli. So on our second pass, which will be much slower and much more accurate, we will equip a drone with a wavelength filtered camera. So this camera will not be susceptible to street lamps and moonlight and things of that sort, but will instead be filtered down to around 450 nanometers, which will be the wavelength that the E. coli give off. From that data, it will be image processed and put into edge detection. We have developed an edge detection algorithm that you can see up there on the right. So that would be an example photo where you have E. coli, and there is a very strong, brighter luminescence of which there is a landmine. From this, based off of the GPS ground station that we have put, as stated earlier by Aiden, we can get accuracy within plus or minus 2 inches of the bomb, of the landmine. And then these coordinates are logged, they're reported, and so they can accurately be diffused in the next steps of the process.
So in summary, our particles and product is eco-friendly because the alginate encapsulates the bacteria, which the alginate is obviously biodegradable and biocompatible, making it eco-friendly. The usage of bacteria and its bioluminescence allows for high accuracy and also underground detection. And due to the lack of human interaction within our system, it also enhances the safety of our system as well.
Yeah, so this is our prototype, as you can see here, of the first plane that we're going to oversight through, which will actually go ahead and drop a set of these bioparticles throughout the system, once it turns on in just a second. So you can see throughout the time, it'll actually spin both the propellers and blades, as well as reset and go through all the motions throughout the flight, because we don't want to just dump them off immediately. We want to do an equal disbursement. So as you'll see here, they'll go and equally turn each of the chambers. It's just a smaller visualization and a mock-up. But it still gets a general idea of going over the whole area. So I want to thank you guys for listening, and we can light up a more peaceful future with biotech. Thanks, and gig 'em. You guys have any questions?
Judges.
Yeah, do you know if there are any natural chemicals that might also trigger your biomarker that could then cause a false positive?
So from the research we have done, they are genetically modified and engineered to just specifically detect DNT and TNT, from what I have read so far. And when they did, from what we read from our research, mainly they did have, most of the trials were successful. There were a few false positives, but mainly they are supposed to detect DNT and TNT.
And that coupled with the image processing would be able to
How wide of an area can you do in one session? And how persistent is your bioluminescence? So if there's some disruption to your process, you can go back to it again, or go back over some long period of time.
Absolutely. So we calculated that based on the density of particles that we need. So for a density of 11 parts per square inch, which is more than enough to go by and scan with an aerial vehicle, we can distribute over 1 acre at a time. And then this would be done multiple times to distribute over a larger area, extremely accurate. We could scale that number up and have a lower density realistically, but to ensure the density, we go with 11 parts per square inch.
We also envisioned almost a fleet of these. And the idea is since it takes 5 hours for the bioluminescence to fully be lit up, we would be, for those 5 hours, we'd be constantly sending out several fleets of these drones going in and then returning and going in and returning, getting a large area and covering a very large area. And that's also part of the design of the drone, is it can go long distances as well. Meant so in case you can't get as close as you'd like to.
So, okay, I got the part where 5 hours where it's sort of, bioluminescent. How long will it stay? How long will that signal be there?
So the E. coli is designed to only survive for 12 hours, and it's encased within this biodegradable material. So essentially, it should die off before the material biodegrades, which that biodegradability duration is about 14 days. If that answers your question.
So it's not lighting up for all that time, but the idea is we also don't want to harm the environment in this, so it's almost gone by overnight. So if you were to do this at 5 p.m., by 5 a.m., anyone who's around would have had no idea it even happened, which is a key part of our safety features.
Right, so I have a question for you. Most of that interaction to get the particles to bioluminescence would be on the dirt to be in close contact with material. What happens when you have a tall grassy field, vegetation that's maybe very dense on the ground? How do you deal with that?
So I believe because of what they're packed in, these actual particles are kind of considered a bit more heavy. I believe, Abram, you can consider this better than I could.
Yeah, so it's made of it has a decent composition of water, so that's why it's supposed to kind of seep a bit lower, which if it were to be in a dense area, it would aid it in being on the ground.
Okay, but then as you fly over, the vegetation is going to obscure your visibility to the particles. They're going to be under leaves, how do you deal with that?
So a huge reason that we chose to use a more drone quadcopter based system for the scanning is that we can then go slower, we can go lower, we have more control over how we are scanning. Additionally, the soil and organic materials are really good at transporting this TNT and DNT. So actually getting the chemical reaction is not an issue. It would simply be an adjustment based on the environment of the scan.
And the question is not about the luminescence of the particle, it's more about line of sight from your camera and your sensor. Given that you're going to have a ground cover, and all the particles are going to be under leaves, under grass.
Alec, do you want to take this one since you brought up the second drone approach?
I wasn't necessarily going to touch on the second drone approach. One thing that we did address with our product design is a specific area of interest. We found that the majority of our landmines, I think there's 20 million still located in areas like Egypt, Yemen, and so the design is more tailored to areas with not dense vegetation and foliage coverage like that.
All right, thank you. Team UXO Minesweepers, come on down, and then Team Paladins, please get on deck. Thank you.
Julie, honey, don't move, okay? Just don't move.
Stay right where you are. Stay very still, sweetheart. You're okay.
Fine. Everything's fine.
Somebody please call for help.
Everything's fine. We need help over
You're
here.
okay, baby. You're gonna be fine. You're all right.
Julie,
Yes.
it's okay.
No, I'm right here,
Don't
sweetie.
With UXO Minesweeper, there finally is. Our system uses a modular sensor suite on unmanned drones and a fleet of unmanned ground vehicles to mark UXOs. The aerial drone uses our machine learning algorithm to identify the locations where mines are most likely to be found and relay that information to ground vehicles at a sensitivity of over 95%. Unmanned ground vehicles search these high-priority areas first to relay exact coordinates of ordnance and mark those locations for civilians using our unique auditory visual feedback system. Together, we will make the world safer with UXO Minesweeper.
As a lieutenant in the South Korea Army and a platoon leader in charge of mine clearing at DMZ, demilitarized zone in Korean Peninsula, I have first-hand experience with danger posed with UXOs. Due to our safety standards, our platoon was only able to cover 9 to 15 square meters a day. Significantly, is smaller than the size of this room. And finding even a single UXO meant that entire searching operation for the day were halted, which with this current system, it will take over 400 years to detect all the UXO in Korean Peninsula. And this is for the most funded, most supported UXO detection program in the world. For countries with smaller operation, where there are more denser minefields, achieving even this level of efficiency is essentially impossible. Manned operation is simply not enough.
So here's the problem, folks. Inadequate detection and insufficient warning measures for UXOs often lead to substantial civilian casualties. In fact, by the end of this Aggies event, we expect there to be more than 3 times the number of this people being affected by UXO permanently for the rest of their lives. Now, a solution to this problem must address 5 key requirements. The first of which being an all-terrain operational capability to withstand any unique environmental challenges. Second, accuracy. The US military defines 80% as operational for wartime. We need to be higher to address civilian rates and give exact GPS locations. Then, efficiency. We need to be able to do this high speed, otherwise we're going to take 400 years and we'll put more civilians at risk. Operator safety is done essentially by using unmanned vehicles and a self-sustaining autonomous path. Finally, but most importantly, the marking ability, not necessarily just for the operators and diffusers, but also for civilians who need to be able to be at a safe distance. This is where our 2-pronged approach, UXO Minesweeper, comes together. We use aerial detection paired with unmanned ground vehicle to be able to identify, detect, and mark UXOs. I'll let Naveed talk about the aerial capabilities.
Our first system is an aerial system that can go to different altitudes, high and low, depending on the vegetation, and is equipped with a sensor suite. It has 3 sensors, a long-range metal detector, an infrared camera, and a LiDAR. The metal detector can detect close to mines with 100% sensitivity with a depth of 60 meters. And 95% of UXOs contain metal that can be detected by the sensor. To detect mines that do not have metals in them, we use an infrared sensor that can look at the mines that are on the surface using the thermal signature. The third is the LiDAR. The LiDAR system, the advantage is it can pass through dense vegetation and can help us identify areas in the terrain using a topographic map that tells us previous detonations that help us go to the exact spot for checking the mines. Our system is very modular. We can just use the same chassis by swapping out the different sensors according to the environment, which helps us manage different environments using the same system. In the first module, what we use is the IR camera plus the metal detector. This module goes at a low altitude of close to 2 feet to the ground, and it can cover an area of 50,000 square kilometers in 30 minutes. And it's useful for areas where there's desert and mountainous terrain, where we can't traverse with a ground vehicle or a LiDAR cannot detect these spots where there's detonations that happen. In the second system, a LiDAR is equipped with a drone that flies at an altitude of 50 kilometers. And this can pass through dense vegetations to spot areas where there might be landmines located. Next, I'll let Nikhil talk about the ground system.
So the ground system will be in addition to our aerial system. Technically, the aerial system goes through the area first and detects the major points of interest that the ground system will then go through and mark specific points of the UXOs. Now the ground system will have a 5-hour runtime on average with an area coverage of half a kilometer squared, and it will incorporate modular components, and overall it will have these 4 sensors. First is the ground penetrating radar and metal detector, which can be used in tandem and have been used before to achieve a 95% accuracy. But our ground system also incorporates chemical and vibrometer sensors that can reduce the false positive rate by over 20 times. And this will get our accuracy to above 99%. And the layout of these sensors are on a ribbon system, which are represented by each of these boxes. And each of these represent one of the different sensors that can be swapped. And the main point of this is to allow for quick, continuous monitoring and swapping of components when necessary. And I'll let Abel talk about that.
So, marking scheme. For marking, we're going to have a 2-pronged system in order to mark these nasty UXOs. The first system is going to use, the land vehicle. This land vehicle is going to go around, mark the UXO using a GPS coordinates. These GPS coordinates will go to the bomb squad, or the GPS operator, which will then transfer it to the bomb squad and safely dismantle the UXOs. Now, while this method is effective, it's not exactly perfect because of civilians, right? I mean, after all, civilians don't have any GPS stuck in their brains. In order to circumvent this issue, we've invented an external machine that is able to be dropped off by the land vehicle. This external machine will give off a loud siren along with a bright light, so that people from many, many meters away can be able to hear this and see it and be able to avoid and run away. This is a good method in order to protect civilians. Now, this external machine won't be able to work in every environment because deserts and maybe marshlands will get wet. So therefore, we've equipped with this drone also a light and a loud siren in cases in which we cannot use it. Next, I'll pass it off to Nish to finish it off.
So we considered many design requirements for what would be our final solution, and it all came down to which achieved these 5 requirements the best. So first, we looked at multi-terrain capability. Every environment that has landmines is radically different, which is why our system is modular, allowing the operators to tailor the sensor suite to what works best in each environment using off-the-shelf commercially viable sensors. Second is accuracy. When it comes to civilian casualties, 1 is too many, which is why we did not go with the aerial system. Any sensor farther away from the target will have lower fidelity and decreased accuracy. Third is efficiency, which is why we did not go with the solely ground-based system, which would take a long time to cover the same amount of area that our combined approach is able to cover. Fourth is operator safety. As our system is unmanned, we can keep the operator safe and monitor a fleet of vehicles. And finally, our marking system. Our marking system is able to warn civilians, often overlooked consideration, as paint, smoke signals, and danger signs are often unavailable to citizens at a close radius. This is why UXO Minesweeper is the best solution for detection of mines. Thank you.
Judges.
So what do you plan to do about the curious civilian who sees a light and hears a sound and says, let me check that out?
Well, typically in the locations that we're going, they have very well-established danger sirens, and we're hopefully planning on incorporating something similar to that in order to be able to use it. Those have already been used in many locations for testings, so a lot of civilians should be relatively well acquainted with how they sound. If we utilize a similar system, then it should be pretty usable. The problems with the alternatives, such as paint, is that essentially, unless you're getting really close, you won't be able to see it. And that too, wind can actually change the location of it. If you're considering desert, wind can move sand. And because of that, sand moving to the side, then you're not gonna be able to do anything. Same problem with smoke detectors, they can only last for so long, and you need to be able to have a solution that's lasting for a long amount of time, such that someone will be able to get to it, but on top of that, civilians will be able to protect themselves by being able to.
Questions. So what's the timeline between dropping the marker and making the light of noise and actually like coming the bomb squad coming to, remove the bomb and silence the marker? And then how do you consider the possibility of maybe somebody sees all this code, making the with lights and sound, like sealing it?
To start the question, I'll let Naveed finish the last part. In order to discuss the timeline, that's what's really nice about our product, because we can constantly have a range, and in the area that we're dropping off the pod, we'll be able to continuously be able to replace it whenever the battery is out, because it's a fully autonomous system that continuously supplies itself. And because of that, we'll be able to essentially have it so that bomb squads can get there at their leisure, while constantly having a system where people are being alerted. And to discuss the flashing lights, I'm sorry, not Naveed, Nikhil, could you get into that reason, please?
Sure. So the sensor will create like a loud pinging sound that can be heard for almost like 2,000 meters away. This pinging sound will happen periodically, not all the time, probably every 30 minutes or so. And that will create enough of a disturbance to anyone that they won't technically take it with them and keep it with them. And it will be completely powered by batteries, and they will be able to last, we are approximating 1 month based on current estimates of battery capacity, but that's almost like how much we're expecting it to last.
It would also be good, it's not like a question, I would say maybe some, what if it would be motion activated, like, that could be a good feature instead of going on and on and on.
Absolutely.
Okay, for your ground-based part of the solution, how do you ensure that you don't inadvertently detonate a mine?
Nikhil, talk about modularity. Sorry, extended modularity.
That's a better answer for
So in our system, what we have is the sensors will be in front of the system. So it will have a standoff range where it will be stationary when detecting the system. So the standoff range it's about 1 meter or so. So when it gets close to that system, and once it detects the mine, it will navigate around the mine so that it can avoid it by accidentally detonating. And it always moves in the direction of the sensor, so it's not going to be in a blind spot where it might accidentally detonate the mine underneath.
A very important thing to note about that, I feel like, is that whenever using systems such as flagpoles or other things that actually go into the ground, you have to consider the surrounding area. And because of that, a lot of land is typically packed close together. So even if you are a meter away, depending on how strong it is, if you push down over there, it can result in tandem force being reached out into that area. By using this arm apparatus, we can actually extend it to a much farther degree. Since this is only a prototype, we couldn't build it to scale. But this should be about anywhere between 1.5 to 3 meters out. So it's actually representing a far enough range for a majority of explosives, as they only require about 2 kilograms to be detonated. And this represents the most optimal distance such that they won't be triggered by having this in a farther proximity.
Okay, one more quick question, judges.
So how many of these alarm systems do you think you can carry in your system? And you mentioned 2,000 meter in terms of the audible range, that's 2 kilometers. Can you explain that?
So the audible range will be like, we'll not only put one of these sensors, we're anticipating to put an array. So that kind of extends both the loudness, the amplitude, and the range. But these sensors we're anticipating to have about maybe 20 to 30. They won't be too large, such that they won't like fit and cause a huge weight gain. But 20 to 30, such that they can have a good operational time of 5 hours, and also be able to be replenished pretty easily as it's a modular system.
All right, thank you. All right, Paladins, please come down.
Howdy!
Howdy.
Come on, guys, try again. Howdy!
Howdy!
All right, well, I like saying howdy too, so howdy!
Howdy!
We are Team Paladins, and this is our presentation on how we spent the last 24 hours developing a UXO detonation and containment system.
This is a Ukrainian civilian who was severely injured by an unexploded ordnance. He, along with many others around the world, know the damage UXOs are capable of.
An unknown number of munitions remain scattered throughout several West Hawaii communities.
Around 85,000 unexploded devices have been found by our unit.
Suffolk officials are investigating after an unexploded artillery piece was found in the city.
In the first half of this year in Cambodia alone, there were 40 landmine accidents.
UXOs can be dealt with by physically moving them to locations where they can be safely detonated. However, this process is slow and extremely dangerous. Without moving the UXO, detonating it in place involves building a barrier around it, which is a manual process that places people dangerously close to the UXO. Therefore, we introduced the Paladin Shield System. It utilizes a shaped charge to detonate the ordnance and employs a multi-layered system designed to minimize blast damage. The shield system is placed by a remote-controlled rover, which allows operators to effectively neutralize UXOs safely.
Howdy, my name is Jared Grimes. I'm a freshman mechatronics engineer.
Howdy, I'm Nisha Fisher. I'm a mechanical senior.
Howdy, I'm Jeremy Lauber. I am a junior in computer engineering.
Howdy, I'm Sarah Buchanan. I'm a freshman biomedical engineer.
Howdy, I'm Lance Fletcher, and I'm a master's computer science student.
Howdy, I'm Charu, and I'm a freshman in computer science.
As shown in the video, unexploded ordnances, or UXOs, pose a serious threat to civilians, military personnel, and even infrastructure. We need a safe system that can be deployed, which will mitigate the damage caused by them, while also eliminating the human interaction while handling them. Utilizing the location found by one of the previous designs that was just shown, our job is then to handle the UXO.
Given that our primary concern is to distance civilians and operators away from the UXOs, we decided on a robotic system that
It's a robotic system that is obviously going to be capable of containing the blast, right?
it's we're using a robotic system to deliver a shield which is placed over top of the UXO that is designed to withstand up to around a half kilogram of high explosives. And the shield is designed to be single use, or the shield and the detonator are designed to be single use.
So we came up with 3 different designs initially. The first one was kind of like a bulldozer, and it moves towards the previously located ordnance and tries to detonate it. But we did not use this one because it had a sacrificial arm and it would not be ever reusable. Instead, we used a deployment device with sacrificial containment system because that is reusable, and the robot can be reused again, and it moves toward the ordnance, places the containment system on top of it, and takes itself out of harm's way. This way, no personnel is endangered, while the dangers of the ordnance is also mitigated. The one that we also did not use is the reusable payload dropping drone, which sends a shaped charge towards the ordnance. However, we didn't use this one because there was no explosion containment.
So, the nature of our device, we have a shielding system which will be placed on top of over the top of the UXO device. We also have a robotic delivery system. So that shielding system is composed of two parts. It has the structure, which holds the whole thing in place. It also has blast-absorbing panes, which dampen and control that explosion. And then the whole thing is operated by a mobile rover that can drive in, place the shield, drive to a safe location, and it's thus very reusable.
The Paladin shield system safely destroys UXOs using a containment system, which is shaped in a very special geometric pattern that allows for air to escape during the blast, while the planes contain the fragments from the blast. There are 8 side planes and plus a lid for a total of 9 planes, and the planes are held together with a 80-20 aluminum frame. The aluminum frame is very versatile and allowing for on-site construction of the product, which makes it very portable. Overall, it's lightweight, inexpensive, and safe, which to meet all of your UXO disposing needs.
So these blast panes, we're going to have 9 of them. They're composed of a series of layers. I have a demo unit here that I'd be happy to start around, pass it across. We're using layered tempered glass and a material called blast wrap. It's developed by Blast Guard Technology. So the two primary methods of lethality for an explosive like a landmine or grenade, etc., would be the concussive blast, the blast wave, and also shrapnel. So this dual system, layered system, is designed to take care of both of those. The blast wrap in texting by Lockheed Martin, a tub lined with blast wrap around an explosion can decrease the overpressure by up to 30%. So that's designed to contain the blast for it. However, the tempered glass is designed, basically the energy from the shrapnel expanding out from your explosive will hit the tempered glass, shattering the glass, turning all of that shrapnel energy into glass shattering. And I'd much prefer to have that than a piece of fragmentation going at 1.5 kilometers per second. So this is designed to protect both civilians and infrastructure. We have a little mock test demo where we have a duplicate. You can see it here. It got hit with a mock explosion. Very fun little experiment, destructive testing. But please go ahead.
Our team chose to a commercial off-the-shelf solution by L3 Harris, and it was chosen because it has 8 hours of operation, as well as it's able to work on
Terrain up to about 30 degrees.
On terrain up to 30 degrees, and it's able to lift up to
Up to about 60 pounds when fully extended. The whole unit costs about $500,000. And then we know that it's reliable and it's something that we could definitely use as a resource. The U.S. Air Force has purchased about 170 of these units to be used by the U.S. Air Force.
Our prototype demonstrates the robot's ability to maneuver around obstacles, and the operator will see through the robot's camera. The operator being able to be controlled remotely makes the robot keeps all personnel safe during the process. Furthermore, the robot is able to secure the container safely over the UXO, and after the container is placed, the robot will exit the scene to a safe distance, and the shaped charge will be remotely detonated. The explosion will be contained in the container, and in the single-use container, and the robot will be kept safe
away from the explosion.
In summary, the utilization of the robust robotic system, along with the uniquely designed shield, which can minimize damage, equates to being able to eliminate and neutralize UXOs in a safer, more reliable manner. Thank you.
Hey, judges.
Do you know what the typical size of a UXO is, and specifically in relation to your limit? You said you have a 0.5.
Yes,
kilogram
absolutely.
limit.
We consulted with the industry professional in high explosives. He said that your approximate landmine is going to be right at our threshold of 0.5 kilograms of high explosives. So that's actually how we defined what that limitation would be. In addition, we can also, due to the scalability and the nature of being able to assemble it on site based on what your needs are, you could definitely add additional layers of shielding.
For larger explosives, you could add more layers.
Okay, not clear to me how you determine where exactly the unexploded ordnance is, and how do you get the accuracy of the arm put down on top.
So we did make a little bit of an assumption that there is already a system in place that properly marks the UXO, whether that be coordinate systems or the tag system that one of the teams had. And we imagined that there would be some sort of integration of our two systems where we could accurately pinpoint it and then utilize that data to actually place the shield properly.
Probably missed this somewhere in the briefing, but what is the shape charge? So we talked about the shield system, but I didn't really catch the shape charge discussion.
So the shape charge, we haven't fully spec'd it out what the exact specs would be. It was a little out of our wheelhouse. We were more focused on the shielding. However, we do know that it would need to be able to penetrate deep enough to actually explode the ordnance if it was buried underground to a certain extent. We imagine that we're dealing with landmines of some sort, so obviously something that packs enough punch to actually penetrate the ground as well as explode the ordnance.
Also, the remote detonation is done via radio waves.
Okay, any other questions from the judges? Okay, thank you. Okay, believe it or not, that was the last team. Students, you did it. Oh, yes, come on, you did it. Oh, very good. Thank you all, thank you all. Okay, so this is time for probably a bio break, probably. Judges, we need to deliberate. And then students, please come back. This is where, while the judges are deliberating, this is where you do the survey of the class. Your feedback is extremely important. Please do that. And then when we are done deliberating, when you're done with surveys, we will meet out here for pictures on the stairs. Okay? This will take about half hour, Fred. 15 minutes, maybe, who knows? And that's it. Students, thank you once again. Wonderful job.
I think so. I was shaking. We gotta go back. I was talking to you.
Please grab a gift here. Eric, there we go. Thank you. Let's go, Bob! Yeah, Bob! Thank you. Without our mentors, this program would not be as impactful as it is. So once again, thank you. Next, we call this the People's Choice winners. So these were by the students who picked these 5 prizes. So each student from the team will receive a $25 in their account. Student account.
Like $90?
That's pretty good. That's not bad. Okay. Most feasible solution goes to Boomhawk. Okay. Best prototype goes to Team Paladin. Where are you? Best teamwork goes to Team Boomhawk. That's good. Best video goes to Team UXO Minesweepers. And then the last People's Choice winners for best presentation goes to Team UXO Minesweepers. I would like to ask the judges to come on up here. Do we have big checks? Yep. Right around the corner here. Yeah, we're going to start with third place. Make sure you grab the third place check. Yeah. Go to the big check.
I always wanted to hold a big check.
So, third place.
Sky Guardians, third place.
Sure, man, take the big picture.
You guys can get one or two, right? Have to buy it.
Yeah, hold that check in front. There you go. There we go.
All righty. 1, 2, 3. Perfect. Thank you.
Alright, so second place, the winner is the Paladins.
All right. 1, 2, 3. One more. And thank you. And the winner is Biotech.
yell.
Here. Yeah. Right. 1, 2, 3. More.
Can we get our mentor? It wouldn't be possible without her.
Oh yeah, of course.
Come on, Krista.
Yeah, please.
Come on.
Ready? 1, 2, 3. And 4. Got it. Thank you. Thank you all. We do have one final special award we want to give out here. This is from the Malloy team here. We want to give out a special award to the mentor that we feel really embodies the spirit of this Aggies event. And Eric. Come on, press, let's go.
That's great. You've been kind of vegan, all right?
Yeah. All right. 1, 2, 3. Ready, one more. Fantastic.
All right. Congratulations.
Two more things. One, if you are interested in entrepreneurship or innovation, you can obviously take some more courses or additional information from the now named Malloy Innovation Program. Obviously, we're here. You can seek us out. And then finally, to our sponsors, if you're interested in working for Los Alamos or internships, please reach out to Dee. Please reach out to your mentors. Thank you once again. Well, we went 20 minutes over, sorry. All right, thank you all. Congratulations. Oh, and please clean up your workstations if you haven't already. Okay? We are not your mom and dad. All right, please clean up. Thank you. If I could get the mentors and judges.